Every morning, the sun rises in the east, travels across the sky, and sets in the west. We watch shadows stretch and shrink, and we feel the air warm and cool as the seasons cycle through the year. But the sun is entirely stationary relative to us. We are the ones moving. Earth spins on an invisible axis from west to east. Because we are physically rotating toward the sun in the morning and away from it in the evening, the sun appears to travel across the sky. Our experience of a single day, sunlight giving way to darkness, is an optical illusion created by a rock rotating in the vacuum of space. Imagine a child spinning on a chair in a dark room while a flashlight points directly at them. The light never moves, but as the child spins, different parts of them drift into the beam and then back into the shadows. This 3D model of Earth shows that exact mechanism on a planetary scale. It takes Earth 24 hours to complete one full rotation. Throughout that spin, the sun constantly illuminates exactly one half of the globe, leaving the other half in complete darkness. Notice this terminator line right here, the exact boundary dividing the lit and unlit hemispheres. At any given second, continents are continuously rotating across this threshold, plunging millions of people into night, while millions of others enter the day. This constant mechanical spin dictates our 24-hour clocks, our biological rhythms, and every cycle of light and dark we experience. While Earth spins, it also travels in a massive, almost circular orbit around the sun. One complete revolution takes 365.25 days, the length of our calendar year. Because summer is hot and winter is cold, it is a common assumption that Earth must be physically closer to the sun during the summer months. The opposite is true. Earth actually reaches its closest physical point to the sun, a position called perihelion, in early January, right in the middle of the northern hemisphere's winter. The actual driver of our seasons is an invisible line. Earth's axis does not point straight up and down. It is tilted exactly 23.5 degrees. A few million miles of distance from the sun does almost nothing to our climate. The precise angle at which our planet leans is what determines whether we experience freezing snow or intense summer heat. Look at Earth in its June orbital position. Because of that 23.5-degree tilt, the northern hemisphere leans directly toward the sun. Solar rays strike the surface head-on, concentrating intense heat into a smaller area and creating summer. 6 months later, Earth reaches its December position. The northern hemisphere is now leaning away from the sun. The solar rays hit the surface at a shallow, slanted angle, spreading the exact same amount of energy over a much larger area. That dispersed energy provides far less heat, resulting in winter. Halfway between these two extremes, Earth reaches the equinoxes in March and September. Here, the terminator line passes perfectly through both the north and south poles. Neither hemisphere leans towards the sun, resulting in roughly 12 hours of daylight and 12 hours of darkness everywhere on the globe. Without that specific 23.5-degree tilt, every location on Earth would have a constant, unchanging climate all year round. The tilt alone drives the shifting weather patterns that sustain our ecosystems. Our solar system also includes the moon, orbiting Earth as we orbit the sun. Occasionally, the paths of these three bodies intersect in a perfect line. When the moon passes directly between Earth and the sun on a new moon day, it blocks the incoming sunlight, creating a solar eclipse. Because the moon is much smaller than Earth, its shadow only covers a tiny fraction of our planet. This shadow has two parts: the penumbra, where only some light is blocked, and the umbra, the darkest inner core. You must be standing directly inside the umbra's narrow geographic path to experience a total solar eclipse. This photograph captures that exact moment of totality. The sky goes dark in the middle of the day, and the sun's corona, its glowing outermost atmosphere, becomes completely visible as a ring of light around the moon. The sun's corona emits intense ultraviolet radiation. Looking at any part of a solar eclipse without specialized solar glasses or a pinhole projector will cause permanent blindness. Conversely, a lunar eclipse occurs when Earth passes directly between the sun and the moon. Earth blocks the sunlight and casts its massive shadow over the lunar surface. Because you are simply looking at a shadow on a rock, a lunar eclipse is entirely safe to view with the naked eye. These events are not sudden disappearances of light. They are precise geometric shadows cast across millions of miles of empty space. The moon takes about 29.5 days to complete one orbit around Earth. Yet every single night, its physical shape appears to change in our sky. The moon is a solid sphere of rock. Like Earth, exactly 50% of it is constantly illuminated by the sun, while the back half remains pitch black. This top-down diagram shows the moon's orbit around Earth. The moon's phases are simply the changing angles from which we view that illuminated half from our vantage point on the ground. As the diagram cycles through the moon's positions, you can see how the geometry locks in specific shapes. As the moon moves, we see more of the lit side, a process called waxing, progressing from a sliver of a crescent to a quarter, a bulging gibbous, and finally a full moon. Then it begins waning, or shrinking, back into darkness. The shape of the moon never actually changes. We are simply watching a shifting perspective as a sphere of rock slowly circles our own. That shifting perspective reaches an extreme during a total lunar eclipse, creating an effect often called a blood moon. This photograph shows the deep red hue of the moon during totality. Even though Earth is blocking direct sunlight, our planet's atmosphere bends and scatters the sun's rays, acting like a giant lens. It projects the reddish light from every sunrise and sunset happening on Earth directly onto the lunar surface. For thousands of years, humans relied on these exact celestial mechanics. The predictable orbit of the moon and the tilt of the Earth dictated when to plant crops, when to harvest, and when to hold ancient solstice festivals. Today, astronomers use the strict mathematical rules of those orbits to forecast eclipses and phase changes down to the exact second, centuries in advance. The patterns in the sky are entirely mechanical. Earth rotates, its axis tilts, and the moon circles us on a fixed path. Knowing this allows you to look up tonight and understand your exact position inside the clockwork of the solar system.